All right, we're going to take a look at our last part. So finding empirical formulas from reaction data. So not just given percentages, but actually looking at a chemical reaction. So the products of a chemical reaction can be analyzed to determine the empirical formula of a reactant. A common practice is to determine the empirical formula of a hydrocarbon based on the amounts of water and carbon dioxide that are formed in a reaction, in a combustion reaction. So example of this would be, say we combust, do this up here. So say we burned methane, CH4. When you burn something, we do it in the presence of oxygen, and it produces carbon dioxide and water. Okay, so we want to be able to take some data from this reaction and determine what this chemical formula is. So the idea is when this burns, if we take a sample and we burn the entire thing, all the carbon from our chemical is going to end up in this carbon dioxide right there. So all the carbon ends up in carbon dioxide. And then all of the hydrogen from this is going to end up in that water. So if we know how much carbon dioxide and water we have formed, we should be able to figure out what this formula is. And we actually can. So let's take a look. It says one key concept in use in these problems is a mole ratio, but not one from a chemical reaction. So we've been used to using mole ratios based on the coefficients of our chemical reactions. But we're going to use a new, it might be a new mole ratio to some people, but it's really a mole ratio that we've seen, it's been there the whole time. Every time you look at a chemical, you've seen this. Mole ratios can also be formed from a chemical formula. So for example, the compound CO2, carbon dioxide, has a ratio of 1 mole of carbon to 2 moles of oxygen. So if we were given, say, 5.4 moles of CO2, and we want to know how many moles of carbon are in that, we can do that. We can do a conversion. We can say, okay, in 1 mole of carbon dioxide, in one of these carbon dioxides, there's 1 carbon. Okay, in this, oh, I wrote CO2 again. I'm sorry. There we go. So, in one of these CO2 molecules, there's only 1 carbon, so we can do a mole ratio there. We could do the same thing and look at the oxygen in this. We could say 1 mole of carbon dioxide, CO2. In it, there are 2 moles of oxygen because there are 2 oxygen written in that formula. So we can use it to actually hone in and specify 1 element in a compound. And we're going to use that idea here. So let's take a look at our question. We're going to look at the example and then we'll go back to the directions. It says naphthalene, the active ingredient in one variety of mothballs, so those used to be used in like closets and stuff to keep moths away, is an organic compound that contains carbon and hydrogen only. So it's a hydrocarbon. Complete combustion of a 20.10 gram sample of naphthalene in oxygen. So they're just saying we're burning this hydrocarbon in oxygen. We're yielding 69.00 grams of carbon dioxide and 11.30 grams of water. So it's telling us exactly how many grams of each of these products we formed. Determine the empirical formula of naphthalene. So let's take a look at this. Our steps, the first step says to use the given mass of one product. So one of our products is CO2. We're going to start with that one. I'm going to go ahead and write it down. Convert it to moles of that chemical. Let's do that because we know how to do that. Grams of CO2, 1 mole of CO2. The molar mass of carbon dioxide is 44.01. All right. Then 2 moles of the individual element in the chemical you are wanting to find. So we know that our hydrocarbon is made of carbon and hydrogen. All the carbon, when reacted, goes into that CO2. So we want to figure out how much carbon is in that CO2. So we're going to go for moles of CO2, and we're going to hone in on just that carbon. So in one of these CO2 molecules, we have 1 carbon atom. So we're just creating a mole ratio there, and we can calculate this. So when we calculate, we get 1.568 moles of carbon. So we know when all of this naphthalene, these 20.10 grams of naphthalene reacted, it contained in it 1.568 moles of carbon. Okay. It says follow the same steps above for the other product to determine the moles of the other needed element. So our other needed element is hydrogen. So our hydrogen is coming from the water. So 11.30 grams of water. We want to change from grams of water. Oh, you guys cannot see that. I'm sorry. Okay, we want to change from grams of water to moles of water. So in 1 mole, molar mass is 18.02. And then again, we want to change from moles of water, and we want to hone in on just the element we want. We only want the hydrogen. Now, we always write just H. We're looking for individual atoms here. So in one of these water molecules, we have 2 hydrogen atoms. So in 1 mole of water, we have 2 moles of hydrogen. So that's where the 2 comes in. So again, we want to calculate, and we end up with 1.254 moles of hydrogen. So at this point, this can look pretty familiar to what we did before. I'm going to flip this over. When we found our empirical formula, we got to a point where we had moles of 2 different chemicals, and what we did next was we divided by the smaller number. Guess what? That's our next step. So it says then, as done above or previously, divide both by the smaller number of moles to find the ratio of one element to the other. So we look at these two. Our smaller number is the 1.254. So we divide that, and we'll get 1 mole of hydrogen. And the reason why we always divide by the smaller one is because we want our smallest whole number we can possibly have as a 1. We don't want to have a fraction. If we divided by the bigger number, we get a fraction. It would be terrible. Way harder. And we do that on the one above, and we get 1.25 moles of carbon. Now, if we look at that, that's not a whole number. It's a little bit off. But 1.25, 1 1/4, we can make that into a whole number. We're still looking at a ratio of one substance to another. So let's take a look how we can do that. We know that this means we have 1.25 moles of carbon for every 1 mole of hydrogen. Okay. If I want to make 0.25 into a whole number, I just want to multiply it and make it bigger. So 0.25 times 4 gives us 1. So if we multiply both of these by 4, we can work this out. So 1.25 times 4 gives us 5 moles of carbon. For every 4 times 1 gives us 4 moles of hydrogen. So there's our ratio, 5 to 4. So we can write our formula C5H4. So this can happen sometimes where we don't get this a nice pretty whole number like 1 or 2. We might get a decimal. You might get 1.5, you might get 1.25, and that's because one of the numbers is odd and one is even, and that's just kind of how the numbers work out. So we have our empirical formula, C5H4. So that's a way we can find that empirical formula from chemical reaction data. Something I will point out to this is our empirical. We don't have enough information in our question to actually find the molecular. I will tell you that the molecular for this is actually C10H8. So we can see that it would have to be multiplied by 2 to get there, but this is our actual answer, is the empirical. And the other thing to look at in our question here was something we didn't use. It said complete combustion of 20.1 gram sample of naphthalene. We really don't care what the sample of naphthalene is for this. It's just telling you how much you originally burned. what we really care about is the products of that reaction, the 69 grams of carbon dioxide and the 11.3 grams of water. That's what gets us through our calculations. We actually never end up using this value. So that's something I definitely wanted to point out. If you're like, but what about the 20.1? Okay, it doesn't really matter. So I hope that helps. Try out your practice, and if you have questions, definitely ask. Thank you.